Okay. So isomorphisms. Okay, so we say that G is isomorphic to G prime. Now, F and only F. There exists a one-to-one correspondence now G, which would map the vertices of G onto the vertices of G prime, and H, which would be a mapping of the edges of G onto the edges of G prime. Okay. Now this last part is actually really important. That preserves the edge endpoint functions. Okay. And now that last part, that last statement right there that says that preserves the edge to endpoint functions is something that people sometimes kind of skip over. I know your book doesn't really address the issue when it talks about, but if you actually go into the solution manual of your book, it doesn't actually reference it, and even within the book, it doesn't reference it that much. But preserving the edge to endpoint functions is actually an important part of that statement. And why is that going to be an important part of the statement? We're going to talk about invariance here in a second, about removing invariance. Invariance inevitably have to do with isomorphisms. Those are structures that if you have an isomorphism, the property is preserved. Okay? And yeah, I mean, that's an easy way to tell that something is not isomorphic. But if you start talking about chemistry and you start talking about isomers, you would assume that an isomer would be isomorphic. No, that is not true. So as an example of this, if I create a tree for C5H12, it's got 3 different isomers that that can be represented by 5 carbons and 12 hydrogen atoms. Those isomers are not isomorphic. And we're going to talk about the reason that they are not isomorphic is because of the reason that they don't preserve the edge to endpoint function. Okay? So that last statement actually is important. Okay, so let's look at an example of something that is isomorphic, and then we'll go into some examples of things that are not isomorphic. Okay. So, if we talk about this structure right here, so we'll say V1, V2, E1, E2, V3, V4, we'll call that edge 3, we'll call that edge 4, and then we'll take a different structure, W1, call that F1, call this F2, and we'll link this over here, and we'll call that F3, I'll call this W3, that would be F4, we'll call that W4 down there. And so we'll call this map G, and we'll call that map G prime. Okay. And now, if we look back at our previous statement, it said there exists a one-to-one correspondence. G would be mapping the vertices of lowercase g, would be mapping the vertices of capital case G to the vertices of capital G prime. So let's see, let's start by just looking at, can we figure out a one-to-one correspondence for this? Meaning that each element of this set is going to be mapped onto an individual element of this set, and there's not going to be any repeats. And so, if I said, all right, where would I want to start? Well, how many vertices does G have? G has 4 vertices, all right, so I would say I need to start with V1, V2, V3, and V4. Okay, and now let's look back at our definition. So G, lowercase g, is going to map the vertices of G onto the vertices of G prime, and we want this to be one-to-one, so that any element of the vertices of G we've mapped onto an element of vertices G prime. Okay. So we're looking for a mapping of this, and so I'm going to do called mapping lowercase g and so lowercase g would map all of those vertices onto W1, W2, W3, and W4. Okay. So this is one of the one-to-one correspondences that I'm going to have to try to figure out. All right. So, just looking at these two graphs right here, what do y'all think V1 would be mapped onto? Which vertex would correspond to V1? W4. Okay, great. So we have a single component of V1 being mapped onto W4. And so that means that if V1 is mapped onto W4, then V2 would be mapped onto W3. Okay. And now this last one is arbitrary because you could go over either one. So let's just map, let's say, yeah, V4, wait a minute. No, I'm thinking about the edges, sorry. V3 would have to be matched onto W1. I did not write it down. That's why I'm getting confused. So V3 would be mapped onto W2, and V4 4 would be mapped upon W1. So we have the one-to-one correspondence between the vertices, and then we'd have to consider, all right, so our definition is that there is a mapping of the vertices onto the vertices of G prime, and that H would be the mapping of the edges upon the edges of G prime. Okay. So we'd be looking for another mapping, and this would be edge 1, edge 2, edge 3, and edge 4. Okay, now this would be our lowercase h, and this is going to have to be mapped upon F1, F2, F3, and F4. Okay. So, edge 1, if I look at this, where is edge 1 going to correspond with? Edge 1 is going to correspond with F4. Okay. So it's going to go all the way down here. Okay. Now if I look at edge 2 right here would be corresponding with F3 right there. Okay, so edge 2 would be mapped upon F3. Okay. And then edge, this one is arbitrary. So edge 3 and edge 4 both connect in the same way, but it's easier just to say, okay, edge, it doesn't really matter. It's arbitrary. Edge 3 to F1 or edge 4 to F2. Okay. Now, in your book, it says this is enough justification for this to be a isomorphism, but truly justifying isomorphism is a little bit more difficult. So, what did we do on this part right here? All right, so when you say we have a one-to-one mapping of the vertices upon the edges and the edges upon, the vertices from one to the other and the edges from one to the other. And then it says, okay, so what did we do right there? We got an existence of a correspondence between the vertices and the edges, and then we have to say that preserves the edge to endpoint functions. Okay? So, let's have a look at our edge to endpoint functions and see if they correspond with our mappings. Okay? So, okay, so if I look at edge 1, that would contain those two endpoints, and then if I went to edge 3, now edge 3 would contain B3 and B4, and edge 4 would also contain B3 and B4. Now, if we look at the edges, and endpoint. Now let's consider our mappings, okay? Now, if we look at the mappings of this, edge 1 is going to be mapped down to F4. So, let's put F4 right here. Okay. Now our edge to endpoint. And if we say edge 2 is going to be mapped to F3. Okay. And edge 3, well, edge 3 and edge 4 map to F1 and F2, but let's follow our scheme that we did right there and said that the mapping H, which goes from edge 3 to F1. And then we said that edge 4 would map to F2. And those two won't matter, and you'll see in a second just exactly why they won't matter. Because preserving the edge to endpoint function for F1 and F2, you see that the edge to endpoint function for E3 and edge 4 are the exact same thing. It's going to be the exact same thing for these two as well. So, we want to say that this has to preserve the edge to endpoint function, okay? So, if we look at this, we have the mapping of H, which is going to map the edges onto the other one, okay? Now we want to make sure that the mapping of G maps the same endpoints to this, okay? So without even looking at the graph, let's look at what we had on the previous page. V1 and V2, let's see where they're mapped to. Okay. V1 and V2 get mapped to W3 and W4. So I'm not even looking at the graph at this point. Okay, I'm just looking at my one-to-one correspondence functions. So V1, V2 gets mapped to W3, W4. Okay. Now, is this true of the graph as well? Yes. F4 is going to correspond to W3, W4. That's the edge to endpoint functions corresponding right there. Okay. Now, F3, according to this statement right here, edge 2 is going to correspond with the second vertex and the third vertex, V2 and V3. Okay. Now, if I look back at my graph, I mean, just this mapping relationship that I have right here, what is V2 and V3 going to correspond with? That's going to correspond with W2 and W3. Okay. So edge 3 and edge 4 are going to correspond with, well, F1 and F2. And so then we're going to have V3 and V4. And just because of the mapping that we did, that's going to correspond V3 and V4 get mapped onto W1 and W2. And so that's going to be W1, W2, and W1 and W2. So, when doing this problem, showing that there is a one-to-one correspondence between the vertices of the graphs and the edges of the graph, and then you also have to really include the fact that your edge to endpoint function is preserved. And so that those two mappings that you created will actually preserve the edge to endpoint function, okay? So, when mapping from one isomorphism to another, well, actually, let me stop this video real quick.